This is Chapter 8, Part 2, continuation of the discussion on quantities in chemical reactions. Here, in this part of the chapter, you will be able to learn about limiting reactants, theoretical yield, and percent yield, and what stoichiometry, which we discussed before, means to the heat of reaction, which is expressed as delta H sub Rxn. The actual yield of a chemical reaction depends on a lot of things. Experimentally, you might lose your reactants. Things happen in processing, and the actual yield itself in any given reaction is usually less than 100%. To be above 100%, you're making product that can't possibly be. In that case, maybe there's contamination or something like that going on. So some of the product does not form normally, and the product is lost in the process of creating it or recovering it or something. Here's the definitions of limiting reactants, theoretical yield, actual yield, and percent yield. Limiting reactants are the reactants that must be completely consumed in a chemical reaction to make the product that you're interested in creating. Theoretical yield is the amount of product that can be made in a perfectly perfect chemical reaction. In other words, nothing is lost. It's going to be what it is. And the actual yield is what you're actually going to produce. The percent yield is the actual yield over the theoretical yield, and it's never over 100. So let's look at an example of titanium combined with chlorine gas to make titanium tetrachloride. If we're given 1.8 moles of titanium and 3.2 moles of chlorine gas, let's determine what the limiting reactant is and the theoretical yield. Here we know that 1 mole of titanium will make 1 mole of titanium chloride. So we have that relationship in the top solution map. And in the bottom solution map, we know that 2 moles of chlorine gas will form 1 mole of titanium chloride. So let's look at this. If we take the 1.8 moles of titanium, multiply by the ratio of that relationship that we discussed for titanium to titanium tetrachloride, we get 1.8 moles of titanium tetrachloride. But if we take 3.2 moles of chlorine gas, multiply by the relationship so that we cancel out the moles of chlorine gas, you'll see that we get 1.6 moles of titanium tetrachloride. And this is the least amount of our product. And so therefore, the limiting reactant for this set of conditions is the chlorine gas. In many industrial applications, the more costly reactant, or the reactant that is most difficult to remove from the product mixture, is chosen to be the limiting reactant. When working in a laboratory, we'll measure the amount of reactants in grams. And you guys have already done this in a previous experiment, I believe, so you're somewhat familiar with all of this. To find limiting reactants and theoretical yields from initial masses, we must add 2 steps to our calculations. So we have to have some relationships in which we have the molecular weight of, or the atomic weight of sodium combined with the relationship that we have from our chemical equation. Now this chemical equation is not balanced. It should show 2 moles of sodium solid to 1 mole of chlorine gas. So you'll see that in this relationship down here, that it's 2 moles of sodium in the top solution map of sodium to 2 moles of sodium chloride, and the molecular weight of sodium chloride is 58.44. So I'll put that to use in what we're about to do, using these masses that we have here of 53.2 grams of sodium and 65.8 grams of chlorine. We do the same thing in chlorine gas, where we have 1 mole of chlorine gas is 70.9 grams of chlorine. Multiply by the ratio of 1 to 2, and the molecular weight again of the sodium chloride. When we do the math on this, cancel out all of the units, numerators from denominators, you'll see that we get 135 grams of sodium chloride if we use 53.2 grams of sodium, assuming that everything else is okay in the reaction. But we will also see that 65.8 grams of chlorine yields 108 grams of sodium chloride. And so that's the limiting amount of the product. And therefore, the chlorine gas, in this case, at 65.8 grams is the limiting reactant. The actual yield, as I mentioned before, is less than the theoretical yield always, because things get lost and not everything forms. So the percent yield is the actual yield divided by the theoretical yield times 100. And if we have an actual yield of 86.4, and we saw before the theoretical yield is actually 108 grams if we have limited the amount of chlorine gas that we use, then 86.4 grams divided by 108 grams times 100 is 80%, and that's actually a pretty good yield. So let's switch gears and talk about enthalpy, which is the measure of the heat evolved or absorbed in a reaction. Chemical reactions can be exothermic, meaning that they emit thermal energy when they occur. That means if you're holding onto a test tube and you experience an exothermic reaction when you pour two chemicals together, the test tube itself would heat up. Chemical reactions can be endothermic, meaning they absorb thermal energy when they take place. And in this case, you might pour two chemical reagents together and the test tube would cool off. The amount of thermal energy emitted or absorbed by a chemical reaction under conditions of constant pressure can be quantified with a function called enthalpy, and that just means heat of reaction. We define the enthalpy of reaction as delta H sub Rxn, which is a symbol for that, and is the amount of energy that flows when a reaction occurs at constant pressure. The sign of delta H Rxn can be either positive or negative, and this depends on the direction in which the thermal energy flows when the reaction occurs. Energy flowing out of the chemical system is like a withdrawal from your bank account and carries a negative sign, while energy flowing into the system is like a deposit and carries a positive sign. Here's a schematic of the energy of reactants and products and how they relate to the type of energy given off or absorbed. In an exothermic reaction, energy is released into the surroundings, so the reactants are at higher energy and give off heat to make products that are lower energy. In an endothermic reaction, energy is absorbed from the surroundings, so reactants at lower energy absorb energy from the surroundings to give products with higher energy. When thermal energy flows out of the reaction and into the surroundings, as in an exothermic reaction, the delta H sub Rxn is negative. So this shows the combustion of methane in this reaction here, and the main component of natural gas is methane. Methane, 1 mole, can combine with 2 moles of oxygen to provide 1 mole of carbon dioxide and 2 moles of water and a lot of heat. It gives off 802.3 kilojoules of heat for each mole of methane burned. So the negative sign tells us that the reaction is exothermic, giving off heat to the environment. And so the magnitude of delta H sub Rxn tells us that 802.3 kilojoules of heat are emitted for 1 mole of methane burned in 2 moles of oxygen. When thermal energy flows into the reaction and out of the surroundings, as in an endothermic reaction, then delta H sub Rxn is positive. The enthalpy of reaction for the reaction between nitrogen, shown here, and oxygen gas to form nitrogen monoxide tells us that because of the sign, the reaction absorbs heat, 182.6 kilojoules for 1 mole of nitrogen combined with 1 mole of oxygen gas to provide 2 moles of nitrogen oxide gas. The amount of heat emitted or absorbed when a chemical reaction occurs depends on the amounts of reactants. We usually specify delta H RxN in combination with the balanced chemical equation for the reaction. The magnitude of delta H RxN, or the value you get for delta H sub Rxn, is for the stoichiometric amounts of reactants shown as written in a balanced chemical equation. For example, if we look at propane, the fuel used in LP gas, propane is C3H8 gas, combined 1 mole to 5 moles of oxygen to give 3 moles of carbon dioxide and 4 moles of water. This gives an awful lot of energy, 2,044 kilojoules of energy. So all of those relationships, 1 mole of propane, 5 moles of oxygen, 3 moles of carbon dioxide, and 4 moles of water, are in relationship to the 2,044 kilojoules of heat emitted. And you can construct ratios to make conversion factors for these. To find out how much heat is emitted upon the combustion of a certain mass in grams, then you have to have the molecular weight of propane, for example, and you know that 1 mole of propane gives off 2,044 kilojoules of energy. An LP gas tank in a home barbecue contains 11.8 times 10 to the third grams of propane. So you can calculate the heat associated with this. Look at the chemical reaction again. Let's set up the equation. Here we have the solution mapped for this with the molecular weight correspondences and ratios and the heat for 1 mole of carbon dioxide. All of this from the balanced chemical equation. If we have 11.8 times 10 to the third grams, canceling out grams of propane and moles of propane by setting up the relationships, we will see that 5.47 times 10 to the fifth kilojoules of energy in the form of heat are given off in a barbecue. That's a lot of heat. Often in the homework that you're about to do for this section, the absolute value of Q, which is Q here shown with the sidebars, is requested. So they'll talk about heats of reaction, and Q actually corresponds to that. And they will use text to describe whether heat is given off or absorbed. So if you don't show a minus sign, then you want to be able to say that the heat is given off, or if you don't show a positive sign, then you want to say heat is absorbed in a reaction. So this is all for Chapter 8. Make sure to do your homework and study the examples there. That'll give you good practice for what you need for your quiz and your upcoming exams. So we'll see you next time to talk about Chapter 10. Bye for now.